All right, recording is rolling. So it is Monday, December 5th. Just for context, we have about 9 students out for FCLE testing, and got a few students from Gentili's class that joined us today. Okay, so I have on your guys' desk, you guys have a page with some conceptual questions, with like 20 conceptual questions. So we're going to do a Kahoot. I know we don't get to do these too often just because we're on the chat for time. But yeah, let's do it today because there's some pretty good questions here. So this is on your desk when you guys walk in. On the other side is an FRQ that I have picked out for us. So we'll see when we get there. Here's some stuff we got lined up for later this week. I'm going to do a live with you guys tomorrow. Look forward to that. I'm going to have you guys do full 5-part AP style write up with that, and then go over the points for you guys. So that's tomorrow. AP Classroom, guys have that done before Wednesday so that we can go over that on Wednesday. We have an open notes in-class quiz on Thursday on rotational dynamics, and we'll start the midterm review on Friday. Oh, I did post a new file over the weekend. I don't know if you guys saw it, but it's a pretty good comprehensive review. It's like a PowerPoint with over 100 slides. Working on that a while. And so starter question right here. Got a turntable for you guys. You guys remember a turntable, right? You guys remember this? You guys remember that? So say this thing is spinning and then it slows to a stop. Right, so exactly what you guys just saw there, right? It gave it a spin and it slowed to a stop. Okay. But say it was spinning at 20 radians per second initially, and it slowed to a stop in 5 seconds. Can everybody answer these two questions for me? What was the angular acceleration? The rate it was slowing down, and what was the angular displacement? Like how far did it turn? All right, who figured out either one of those? Either one of those. Anybody figure out the angular acceleration? Yeah, let's get. All right, and then the units are
radians over second squared.
all right. Yeah, Marco's got -4 radians per second squared. I mean, of course, it would be negative if it started in the positive direction and then slowing down, right? You guys are referencing these kinematic formulas, right? Okay. So, which 3 kinematic formulas do you have, or variables do you have? Yeah, you know the initial angular velocity, right? So that's this right here. You know final angular velocity, that's 0 radians per second. That could be that. This should be 0 right there. Right? And you also know the time interval, 5 seconds. That's that guy right there. So you can solve for alpha, right? So 0 equals 20 plus alpha times 5, right? And then units, right? So subtract over 20 divided by 5. Guys, what's -20 divided by 5? -4, and the units would be radians per second squared. So everybody's got -4 radians per second squared, right? Okay. All right. Follow-up question. How far did it turn in radians? Yeah, so Scarlett's saying 50 radians, right? 50 radians. Right. So for that, you have to use one of those other kinematic formulas. You could have used theta equals omega naught t plus half alpha t squared. That's analogous to x equals v naught t plus half at squared. Okay, let's try it this way. So here's the number of radians that we're solving for. Okay. We know it was rotating at 20 radians per second. We're going to go 5 seconds plus 1/2 -4 radians per second squared. And then 5 seconds shows up again squared. See, 5 5 is 25 times 4 divided by 2, -50, 100 minus 50. That's 50. And then the unit is radians. Okay. Or you could use omega final squared equals omega initial squared plus 2 alpha theta. Could have done that too. Right? If this is 0, this is it 20? 20 squared is 400. Subtract that, gives 4 is 8. So if this is okay, 0 equals 20 radians per second squared plus 2 times -4 radians per second squared times theta. Okay, so 20 squared, subtract that over, divide by -8. Yep, same thing. Theta is still equal to 50 radians. Okay. You know how else you could have solved this is actually without using these equations at all. You could use the graph. You guys remember graphs, right? We've got omega in radians per second versus time in seconds. Okay. Here, can you guys draw that graph before I do for that scenario that we just did? Okay. Like here's the starting information. You guys know that alpha is -4 radians per second squared. You figured that out already, right? Okay. How does that map onto that set of axes? Can you guys do that? Omega versus t graph? Let's say time 0. I know this thing was rotating at quick walk around the room, make sure you guys are getting this. Yeah, you just find empty desk. Okay, so you're from Mission Gentilis class, right? All right. Oh, all right. I see Leonardo's got it for sure. Yeah, Rod's got it. Todd's got it. Haley's got it. All right. You guys get this. You guys get this. All right. So you guys said it starts at 20 radians per second. And then it slows down to 0 radians per second. And it does that in 5 seconds. Okay? And it slows down uniformly. That's why it's straight line like that. It's kind of like a triangle shape. Oh, you guys, what property of that graph would also tell you how far it rotated? The area. Yeah. So okay. So the slope does tell you something. The slope tells you angular acceleration, right? Which is your -4 radians per second squared that you guys figured out. Okay. But how about this area? Okay. You guys said the area tells you how far it rotates because radians per second multiplied by seconds. Okay. Rad per second times seconds gives you number of radians. Okay. And area of a triangle, 1/2 base height. So 20 times 5 is 100. Divide by 2. Oh, is again 50 radians. So there's 3 different ways to get to angular displacement of 50 radians. Right, you guys got that? All right. All right, so it's nice kinematic motion review. All right, you guys got your phones out for Kahoot. All right, so we're going to do some conceptual questions. Flip my screen over here. All right. Again, if you're in Mr. Gentili's class, there's one more shot at that. Right, so does everybody have that? If you're in Mr. Gentili's class, you guys figured that information? All right. Let me get it. Ooh. We find some for you guys here. It's over. All right, let me flip my screen, share screen 2. There we go. All right. Real fast, I do want to show you guys. I've uploaded a few files for you guys under midterm review, which we're going to start this Friday. One of them I put over this weekend. It's big old PowerPoint. So I've been working on those last few weeks for you guys. So flip this real fast. We got scientific method, measurement, algebra stuff, geometry stuff, kinematic motion, dynamics, free body diagrams, some kinematic rotational stuff. There's orbits, centrifugal force, energy, momentum. Bam, it's all here. And then the recent rotational dynamics. So that is on there for you guys. It's pretty long. All right, let me find Kahoot. All right, so the conceptual questions you guys have printed in front of you guys. So punch in the pen. Here you go. All right, got everybody on. All right, so here we go. Torque. All right, I'm going to stop some of these early because you should know by about now, right? Yeah, force times lever arm, right? So this is like turning a wrench, opening a door, right? So you need a lever arm crossed with a force. It's not R crossed up, force times lever arm, lever arm times force. Right? And you really care about the perpendicular components too, right? Perpendicular components. All right, Scarlett, is easier to loosen a nut with a wrench if you do what? Yeah, those are all good, right? So exerting a larger force will definitely help. Also extending the lever arm, right? Right. Give you more leverage. Right? You push at the end of the wrench. Right? Isn't that why the door handle is opposite of the hinges? Right? Why isn't the door handle in the middle of the door? Oh, because that right. But also, you only care about the perpendicular components. So as long as you push perpendicular to the lever arm, right, you're maximizing your torque. That's what the sine theta part's about, right? Those are all true. All the above. I've got Scarlett, Nick, Bill, Michael, Iska. If a football is kicked, so through the center of gravity, what's that ball gonna do? Uh, yeah, it should here, flip the screen, draw this up for you guys. Let's see this one draw. Brown, football, center of mass, center of gravity. Okay. So if you kick it down here, isn't it gonna like tumble this way? Counterclockwise. If you kick it right here, it's gonna tumble clockwise. But if you kick it right through its center of gravity, it's gonna take off without rotating at all. Oh, Nick, moving top spot. Resistance an object has to changes in its rotational state of motion. Yeah, rotational inertia. Right. So you guys remember? This rotational inertia table? Or you guys remember those 2-meter sticks that passed around class? Right? Right? Had the exact same mass, exact same weight, but they were taken on different places. So that different difficulty and shaking them back and forth. Right? So different resistance to some kind of rotational motion. Okay. Where's my roller race? Here we go. Right? So it's really hard to get this guy rotating the ring. It's really easy to get the bowling ball rotating, right? Like per equal mass, right? Okay. But even if those were different masses, the race would still play out the same. All right, Nick is still in the top spot. Which has more rotational inertia, a bike wheel like a ring or a solid disc? Same mass, same diameter. Yeah. All right. All right. So unless you guys got it, the wheel. Here, let me remind you guys. Okay. So say you're comparing these two. Right? Let's say same mass, same like radial size, right? Uh, wouldn't this have like every single point would be mr squared? If you added up, the aggregate effect is mr squared for the entire mass, right? But for the solid cylinder, right, is it more of its mass distributed closer to the center? Right, it's kind of like that meter stick with the weights taped like closer in. It's easier to rotate, right? So actually, it has ends up having half the rotational inertia of the ring, right? Okay, guys remember that too. All right. IO, Braden, Elijah, Scarlett, and Nick. Which has more rotational inertia? Yeah, right. Because like if you run normally and bend your legs, isn't like the mass of your legs getting closer to your own center mass, which would actually decrease your rotational inertia, right? But if you keep your legs straight, that's like a wider distribution of your mass, right? Kind of like the ice skater, where they're like more like spread out, right? Have more rotational inertia for the blue one. Solid cylinder will roll down an incline with greater acceleration than a hollow cylinder if yeah, none of the above are necessary. So if you directly compared the rotational inertias, just a straight up value, then mass and radial size would matter. But if it's more mass, then you guys know that also means like more force. But it kind of goes back to the idea of why all objects free fall at the same rate, even though the different forces, different masses, but that cancels out. Same thing here. So like that race with all those really objects rolling down the incline, what really matters is the distribution of the masses. So the ring will always lose the race, right? And then like the bowling ball is usually going to win. Right? You guys go with that? Here, let me flip the screen over and show you guys that really race again. Right. So this really race here. Right? Now, if they're all like equal masses or equal radial size, then it's a really obvious comparison. But even if they're different masses and different sizes, like if I had a marble next to a bowling ball, right? Like a marble and a bowling ball, they're both like solid spheres. So those would go pretty well like side by side all the way down. Those would probably tie, like the marble and the bowling ball. Because the distribution of the mass is the same. I got IEO on fire. When a gymnast moves from an extended position to a tuck position, ooh, reminds me of the ice skater. Plays gymnast with ice skater. I think you have the same principle going on. Yeah, there you go. Gonna decrease your rotational inertia. So give you guys the picture for that again. And that might cause something else to happen too. Right? So you go from a sit position to tug position. Aren't you like decreasing your rotational inertia? Like your mass getting closer to this axis of rotation? Okay? Now, if she's rotating at the same time, what happens to her angular velocity from left to right? It's going to go up, isn't it? It's going to increase. Right? What if her rotational inertia gets cut in half? What happens to her angular velocity? Twice as fast. Now she's spinning twice as fast, right? Because angular momentum is conserved, right? Elijah on fire, Braden second, IEO, top spot. When an ice skater pulls his hands to turn in faster. Ooh. Yeah, those are all true, right? So angular momentum is conserved, rotational inertia decreases, and rotational speed increases. Right, those are all true. Okay. Hey, what about something that's not asked up here? What about rotational kinetic energy, 1/2 I omega squared? What do you think happens to that when you pull your hands in? Rotational kinetic energy. Here's a hint. Does it take some effort to pull your hands in? Is that a force? Force times distance? Ooh. So would the side skater be putting some work into the system, thereby doing what to the energy of the system? Increasing, right? And formulaically, I mean, if I times omega is conserved, 1/2 I omega squared, right? If you decrease the I but increase the omega, that squared part counts more. Yeah. So for however you look at it, the rotational kinetic energy is going to go up, isn't it? Ooh, Braden to the top. Large rotating cloud in space shrinks in size, right? It's like gravitating closer together. How's it spinning? Yeah, it's got to rotate faster, right? It's the exact same principle as the ice skater. Rotate faster. Braden, extend the lead. When one person leans toward the center of a seesaw, what will that end do? Leans in toward the center. Ooh, all right. Most of you guys got that? Draw this out real fast. So suppose you got a seesaw, it was balanced. These guys are, say, same mass, same weight, same distance from the pivot point, or like pretty close to. So they're causing the same torque about this pivot point, right? Okay. Now, what if this guy like leans in? And I'll make it more obvious by what would it be like physically like scoots in, right? Now, torque, you guys know, is R cross F. So no, the forces haven't changed. The masses of the forces haven't changed, right? But its radial size from this pivot point definitely has. Right, so that's a lot less torque from the point of view of that pivot point. Therefore, this whole thing's gonna rotate that way, right? Just like that. Elijah on fire, IEO, back to the top spot. To turn a stubborn screw, it's best to use a screwdriver that has a what? This is not a wrench, this is a screwdriver, right? So different tool. Oops, I should have given you guys that hint faster. Right. So we're not talking about a wrench. We're talking about a screwdriver. Okay. Right, so right here. And so we're looking at like this, right? Okay. Now the wrench, you definitely want a long wrench. The long wrench will help you, but a screwdriver, if you're looking at torque equals R cross F. Okay. Here's your radial size right here. That's your R, right? Okay. And the F is like maybe a frictional force between like your fingers in the handle. Okay. So there's some force here. F, right? R cross F is like that, isn't it? Is it? Yeah. So you want a wide handle for a screwdriver. Oh, all right. Legend IO picking up points. A ring and a disc roll down a hill together, which will reach the bottom first. Yeah, the disc, because it has less rotational inertia. Flip the screen over real fast. Bam, you guys remember that right there? That ring race? Right, so the ring always loses because it has so much rotational inertia. Right? Right. Hey, that ring that's losing the race has rotational inertia just plain mr squared, right? Okay. And all the other ones have something less than mr squared. Can you have a rotational inertia that's more than mr squared? Is that possible? I'm thinking, what about this? What if you had like this type shape and you prop this up like right here, like on my hand, okay? And let it roll down. Or here, what's better? Put something here better. How about on this roller? What if I put this roller right here and I just let it roll down the roller? Well, the fact that there's so much mass like outside of what it's rolling, I bet that could possibly have rotational inertia more than mr squared. Maybe something like that. IO, keeping the top spot. Why does the ball gain speed as it rolls down the incline? Yeah, that's all part of the story. Okay. In fact, if there was no friction, would it even roll? No, it wouldn't even roll without friction. So you need static friction, and static friction is the best because if it's kinetic friction, it's like slipping, it's taking energy out of the system. It's like But if it's static friction to just induce rolling, okay, that'll allow a torque to set up on it. Right? There's a force, outside force. Okay. At different orientations, the cams provide different. If I'm pulling on that rope on the right, feels all wonkety. Yeah. Right, so yeah, you'd have different lever arms as you're pulling on the one on the right, because right, sometimes it's closer to the axis of rotation, sometimes further away. Right. And if that's true, if you wanted, say, like a constant torque, you'd have to change the force. Here, flip the screen over. You guys remember? Hey, you guys remember that, right? So torque is R cross F, right? Back over here. Yeah. All right, we got Studi, Nick, Braden, IEO, and Elijah to the top. Which way will the spool move? There's like a ground down here too, right? I should have drawn the ground. So pull to the left, which way does the spool move? Yeah, towards you. Right. Yeah, just go here. Let's check this out. Got this going on. Right. Yep, it's definitely to the left. Pull to the left, it goes to the left. So counterclockwise. Oh, from my point of view, I guess, right? All right. Follow-up question. Turn it upside down. There's still a floor down here, right? So there's a static friction point, static friction at this point. So we're still inducing a torque pulling to the left. Gonna move off to the ooh, it's still the direction that you pull it. Okay. So whatever force that you apply will end up being the direction of the net force. Right. So here I've just turned this upside down, right? You guys see the string down the bottom now? Right. Oh, I pull to the left, it still goes to the left. Right? It's still the same, like from this point of view, counterclockwise motion. Right. All right. Braden, Stuti, Nick, IEO, and Elijah. A few questions left. Where should a 30 Newton weight be placed so that the meter stick will be balanced at the 50 centimeter mark? Where should you put a 30 Newton weight? Ooh, all right. That's a tough one, looks like. All right, so why 60 centimeters? All right, so I'll flip my screen over and show you guys why. Now, you guys did a 2-day lab on this, and from that, you guys know you can pick any point as like a pivot point or something to torque about. But sometimes there's a most obvious point. I really like this point right here as treat this as the pivot point. Right? One reason why is that I know there's a huge upward force here. Right? It has to hold this 10 newtons plus the 30 newtons we're going to stack up. So there's like at least a 40 newton upward force. Maybe the meter stick itself has some weight. But if I pick this point as the pivot point, then the torque caused by the force at that point is 0. Because it's like pushing on the door hinges that will never turn the door. So I'm going to pick this as my pivot point, and that is going to greatly simplify this whole problem. Now the answer.
Hi, part of the interruption, but could all teachers allow the early college students, 10th graders, to report to the front to wait for the bus for 9:25? Again, early college students, 10th graders, report to the front at 9:25 to wait for the bus. Thank you.
All right, anybody got to go to college? No. All right. So here, this ends up being the answer, right? So let's take a look in terms of torque is equal to R cross F. Okay. You guys see here, guys, what's this lever arm right here?
30.
Yeah, 30 centimeters. What's 30 times 10? That's 300. right? Isn't this torque equals 300 Newton centimeters? 300 Newton centimeters, right? What is this 30 times this 10? Is that also 300 Newton centimeters? Except, let's see, clockwise, well, if I do right hand rule, it ends up being negative, so call it negative, right? Ah, and now that's a wash, right? Because that'd be zero torque. Hence it would balance the problem, right? We balance it, right? It's like a third of the distance, 3 times the force, right? Elijah keeping the top spot. Got IEO, Brady, and Nick. Ooh, Samantha on fire. Top 5. In order to increase his or her rotational inertia, a tightrope walker can carry a long stick. Yeah, that is true. Here. All right, so I got 2 sides of a cliff. Here's the valley between them. Right. So cliff. Okay, here's a tightrope going across. There's a guy trying to walk this tightrope. Okay, which is pretty hard to do, but what can definitely help you a lot is to carry a long stick, long pole. Okay. Because when that increases guy's rotational inertia, right? It's kind of like here. You guys remember like trying to balance a meter stick? Okay. Like you can do that because it has so much rotational inertia. It's not too hard to balance. Okay? If you have a meter stick. So same thing here. If he gets knocked off a little bit, starts to fall over, well, he has so much rotational inertia, it's pretty easy to correct his balance before he actually falls. Yeah, carry a long stick. All right, Alex, hop in the top 5. Elijah, hold on to the lead. Last question for the win. A short pendulum has more rotational inertia than a long pendulum. Equal masses. All right. So those guys got that. Said false. Let's look at why, and then we'll go to the winner's podium. So you guys remember for a point math that MR squared, right? So we got maybe like R1 and R2 or L1 and L2. Okay. Yeah, if they're equal masses, okay, that checks out the same. But you guys see that this one here, relative to this point, it's rotating about, has, well, larger R, right? In fact, if the R is twice as much, suppose it's like 10 centimeters, this is 20 centimeters. If it's twice as much, how much more rotational inertia?
4.
4 times. You guys see 4 times? Because a factor of 2 squared is like 4 times, like I said. Oh. All right, let's check out our winners. With the bronze, for Aiden. With the silver, IEO. And the gold, Elijah. Oh, yeah. All right, runners up. Got Nick and Alex. All right, nice job, guys. All right, let's flip back over here. Okay, got about what, 9 minutes? I think we can do a fast version of this FRQ. Whoops.